In this lecture, we're going to solve 3D particle equilibrium problems by drawing a 3D free body diagram and applying the three scalar equations of equilibrium. Some example problems that we can solve with 3D particle equilibrium. So here's one example. If we know the weight or forces down here, we can solve the forces developed in each chain to see if it is a safe assembly. In other words, we can find end forces, but the difference between this lecture and the last lecture is your assembly is no longer within a piece of paper or in the XY plane. It's not a planar assembly. Now you will have X, Y, and Z axes. We also see some simple design questions. Maybe you're asked to find the maximum weight can be suspended by the structure, or sometimes you may be asked to find a certain distance to make sure the structure is safe. But overall, again, the key point here is the assembly is no longer just within the XY plane, but now you have a three-dimensional problem. And that's the topic for this class, 3D particle equilibrium. When a particle, like this particle over here, is in equilibrium, the vector sum of all the forces acting on it must be zero. So if we write it into equation, the sum of all the forces exerting on this particle must be equal to zero for the particle to be in equilibrium. And we learned from the last class, from your intro to engineering problems, that each vector can be written into component format. And now we have X, Y, Z axes. So in a 3D or three-dimensional space, this vector should have each vector should have three components, and we gather all of the components together. So this sum of the vector can be written into component format as well. So the resultant force equal to the x component of the resultant force is the sum of all the x components, and y component of the resultant is the sum of all the y components, and the z component of the resultant force equal to the sum of the z components of all the forces. And this formula is called the vector formulation for 3D equilibrium problems. Now from the vector formulation showing here, we know if a vector is zero, then each single component of this vector must be equal to zero. Means x component is zero, y component, and z component, all of the components need to be zero. So from the vector formula, we can write three scalar equations. So these are the three scalar equations. Sum of the x components must be equal to zero, sum of the y component must be equal to zero, and sum of the z component must be equal to zero as well. And this set of equations is called the scalar formulation. And we're going to use this set of equations to solve 3D particle equilibrium problems. So if you compare this set of equations with the equations we learned from last lecture, the 2D equilibrium, the only difference is we have one actual equation, which is sigma fz equal to 0. In 2D, we don't have the third dimension, usually the z-axis or the z component. But in 3D problem, we have one additional z component equation. So if in 2D equation, 2D problems, we can solve up to two unknowns. Now in 3D problems, we can solve up to three unknowns with one particle, with one free body diagram of a single particle. Let's see one example. We have the assembly showing to the right, and the four forces and geometry are shown. Now we're looking for the tension developed in cables AB, AD, and AC. And we have one given force, 300-pound force, pulling down at point A. So to solve this kind of problem, we're still going to follow the two major steps. The first step is to draw the free body diagram of the particle A. Again, that particle usually is the concurrent point of all the forces. Then we're going to express all of the forces in Cartesian vector form and use the three equilibrium equations to solve up to three unknowns. So let's see how to solve this one. So here is the given information, and we're looking for the tension developed in each cable. So keep in mind, cables can only exert tension, which means can only pull from the point, cannot push into the point. And the direction of the tension developed in the cable is along the direction of the cable, meaning here is my TB pointing from A to B, and since everything's starting from A, so I just omit the A, use B, means it's pointing to the B, and the TC is the tension developed inside this cable AC, and TD is the tension developed within the cable AD. And we are looking for those three forces. To be more specific, we are looking for the magnitudes of the forces. Why? Why magnitudes only? Because if you take a look at the figure, we already have those geometry or those angles given. With those angles, which means the direction of the cable is already given, or the direction of the vector is given. So we only need to know or to find out the magnitude of the forces. So to solve this problem, equilibrium problem, the first step is to draw the free body diagram. And in this case, we're going to draw the free body diagram at particle A. So we put point A as a point, or particle A as a point, and this point will be the origin of the coordinate system. So we have X, Y, and Z coordinate right now. And after that, we're gonna isolate this particle from all of its surroundings, which means we're gonna remove all of the cables. We have three cables, right, contacting with point A, AB, AD, and AC, but we're gonna remove all of the cables, but only put the forces exerted by this cable at point A. So the first one is the 300-pound force pulling to the negative Z direction. And for TB is just directing along the X and positive X direction. So this is the TB. And for TD is pointing up into the space, is not along any X, Y, or Z direction, but it has those direction angles that you want to put it down to help you write this TD in Cartesian vector form. For force TC, similar idea, we're gonna draw it on this free body diagram from point A to the point C, and this is the TC. And I'm not going to draw those projection triangles on this figure, otherwise this free body diagram will be so messy. We'll refer to the original given information to write down the TC in Cartesian vector form later. So now, free body diagram at point A is done. There are four forces exerting at point A with one given value. All the other three values are not known. So the second step is to write the equations of equilibrium. But before we can write equations of equilibrium, we need to write each force in Cartesian vector form. So express all the forces in component form or Cartesian form. So let's take a look at TB. So force TB, since it's vector form, we need to write TB as a vector. Okay, use the right notation, please. And now TB, we have the direction, right? TB is pointing directly into the positive x direction. Therefore, with the unknown magnitude which we're looking for, a vector equal to the magnitude times the direction. Direction is just I hat. So now TB equal to magnitude of TB times I hat. Now for vector TD, we already have those direction angles, but be very careful with the given angles. 120 degree. So the 120 degree, if you see, is just the angle between TD and x-axis. So that means alpha is 120. So we can write that down. Alpha 120. How about beta? So keep in mind, beta is the angle between the positive, the head of the vector and the positive axis. So now 60 degree actually is the direction between the head of TD and the negative y-axis. Therefore, 60 is not beta, but beta should be 180 minus 60. So it should be 120 degree as well. And then gamma is the angle between the positive z-axis and the head of TD, which is 45, the given value. So with those direction angles, we can then write TD in vector form. So it becomes TD, again TD, magnitude doesn't know, cosine alpha, that's the x component of TD force, and TD cosine beta, well, we should put down the values directly here, and TD cosine 45 k hat. The last force is the TC, and we have been working with this type of vector couple of times from your assignment. So let's take a look again. We need to find the components of TC, right? Assume or use the TC, the magnitude, that's the unknown value. Now we need to find the x component, y and z component. Let me find a different color. So from point A to point C, we travel along the y direction, simpler. So this is at cy. And then along the x direction, c of x. Now you can see cx actually is a negative scalar component. So I will put a negative sign to remind me. And then lastly, travel to the head by traveling along the z direction. And that is the CZ. And next we're going to use trigonometry to figure out the relation between the components and the TC. So add this C prime to help us resolve this TC into three components. So in the vertical triangle, you have CZ equal to TC sine 60, and C prime is TC cosine 60. And now then we move down to the triangle in the xy plane to resolve the cy and cx. So cx is negative C prime times sine 30. So it'll be TC, actually should be negative TC. Again, do not forget the negative sign or you will run into errors. Cosine 60 times sine 30, and the C of y will just be TC cosine 60 then cosine 30. Okay, so with those components, with CZ and C of x and C of y, we can easily put TC into vector form. Okay, so this is my TCx, TC of y, and TCZ. Okay, so we now put or written 3 annual forces into vector form, and the direction is given based on the trigonometry, and the only thing we don't know now is the magnitude. So that means we only have 3 unknowns, TB, TC, and TD. Now let's plug in, do some simple calculation to simplify those equations. Okay, so now my TB is just a TB I hat. There's nothing to be simplified. And now after I do I calculate the cosine angles. So here is the TD and the TC as well. Here's the TC. And do not forget, we do have a force applied at particle A, which is this known force, 300-pound force. So all of the forces applied this particle sum up into 0. So don't forget the known force. We want to write that force here as well, so we don't forget it. Let's call it the weight. Okay, that's the weight pulling down, which is 300, or you can do a force as well, is pulling to the negative z direction, so it will be negative 300 k hat, and that's the last force exerting on this particle A. So the next step will be applying the equations of equilibrium. So to make things easier, I'm going to put down the coefficients or the components into a pair of parentheses for you to see, easier for you to see. So meaning I'm going to do this. So this is the force TB. We have I hat is TB, right? The x component is TB, y component 0, and z component is 0 as well. And for the force TD, the next one in the row, we have the x component or the I hat coefficient negative 0.5 TD, and y component negative 5.5 TD times TD means, okay? And the key component is 0.7071. I think I missed the TD on this one. All right, so the next force we have is TC, and TC has x component is negative 25 times TC, y component 0.433 TC, and z component 0.866 TC. Lastly, we have this weight, the given force, which is equal to x component 0, y component 0, k component negative 300. We know it's pound force. Okay, put in here. So remember from the equilibrium condition where the sum of all the forces in vector form is 0, will give us 3 equations of equilibrium. They are sum of fx equal to 0, sum of fy equal to 0, and sum of f of z equal to 0. So that's why I put all the coefficients or the x, y, z components into the columns, and for me to easily add them together. And also don't make mistakes, because some of the forces just have one component instead of 2, right? So you want to put the component into their corresponding positions, so when you add them to write down the equation, it's easier for us to do. Okay, so the fx, which means the I hat column, so we're going to add all of the x components together, which will be TB minus 0.5 TD minus 0.25 TC and plus 0 equal to 0. And next one, we have negative 0.5 TD plus 0.33 Tc equal to 0. And the last column we have 0 and then 0.7071 Td plus 0.866 Tc minus 300 equals to 0. Okay, we have I'm using too many 1, 2, 3s. Well, still need to use 1, 2, 3. So this is equation 1, equation 2, and equation 3. We have 3 equations. We have 3 unknowns, right? We have this TB, TD, and TCs as 3 unknowns. 3 equations, we can solve 3 unknowns. Well, to be fair, to solve the problem is not the scope of this class. It's from your algebra or math class, right? So you need to know how to solve linear equations. But now, let's just take a look at this problem now, how to solve it easily. First, before you start to solve your problem or a set of equations, you probably need to take a look at those equations. A lot of times, those coefficients before the unknown values are kind of related. For example, if you take a look at equation 2 and equation 3, those 2 equations both have two unknowns, Tc and Td. Right? Equation 1 has a third unknown. So probably want to start with equation 2 and equation 3. And from equation 2 and 3, please first you want to check the relation between the coefficients of the same variables, for example, Tc. Right? So in equation 2, the coefficient of Tc is half of the value of equation in equation 3. So that means we can solve Tc and Td from those 2 equations if we, let's say, from equation 2, we can do 0.433 Tc equals to, okay, we're going to move negative 0.5 Td to the other side of the equation, so it will become 0.5 Td, right? And then we multiply this equation by 2 on both sides. You will have 0.866 Tc equals to Td. Okay, so you don't need to do approximations, a lot of calculations. It's easy, isn't it? Okay, now if we substitute, let's call this 4. Substitute equation 4 into equation 3. We will have 0.7071 Td plus Td minus 300 equal to 0. So Td can be solved. And we plug this value back into equation 4. So Tc is Td divided by 0.866. So Tc is solved to be 203 pound-force. And we substitute both values into equation 1, then we can solve Tb, and Tb is 139 pound-force, and the problem is solved. Okay, take a look at this solution one more time. So usually to solve equilibrium type of problems, we need to first draw the free body diagram. Second, based on the free body diagram, we're going to write the equation of equilibriums. But for 3D problem especially, in order to write equation of equilibriums, we need to express all the forces in Cartesian form and then add their corresponding components together to let them equal to 0. So we will have 3 equations. And check your equation, check number of unknowns to see if you have enough equations to solve all of your unknowns. If not, maybe we need another free body diagram to have another set of equations.